Here's a couple more examples where we want to determine whether the sequence converges or diverges. So with this first, here's the first one. 1 plus negative 1 to the n all over n squared. So what I would do with that one is split up that numerator. So make this 1 over n squared plus negative 1 to the n over n squared. And so now when we want to take the limit of the terms in this sequence, we could look at this if we want as two separate sequences. That's one of your properties of infinite sequences, is that the limit of the sum of terms here is equal to the sum of the limits. Which is really just to say, so if we want to take the limit of the terms in this sequence an, we're allowed to look at this separately. Limit as n approaches infinity of 1 over n squared plus the limit as n approaches infinity of these terms, negative 1 to the n over n squared. So in this first piece, just this is 1 over infinity. Any limit of the form finite number over infinity is going to 0. So this first piece is definitely going to 0. The second piece here, so this one's alternating signs. If the terms in this sequence, if we write them out, if we start with n equals 1, this will be negative 1 over 1 squared. N equals 2, this will be positive 1 over 2 squared, which is 4. N equals 3, this will be negative 1 over 3 squared, so negative 1 over 9, and so on. So we've got alternating terms. We could use the alternating sequence theorem, which we just proved. So if we take the limit as n approaches infinity of the absolute value of these terms, negative 1 to the n over n squared, the absolute value of negative 1 to the n is 1. Because keep in mind, this is either positive 1 or negative 1, depending on if n is an even number or an odd number. But so if this is always plus or minus 1 and we take the absolute value, that's always going to be 1 over n squared. N squared will always be positive, and so the absolute value is just n squared. And so now this has the form 1 over infinity, so it's approaching 0. So this piece right here, by the alternating sequence theorem, is also approaching 0. And so this sequence converges to 0. Converges to 0. Okay, so example 2 over here. Cosine of n over n cubed. If we take the limit... Well, so if we try to take the limit as n approaches infinity, let me write that down, of cosine of n over n cubed. Now keep in mind, cosine of n oscillates. Picture the graph of y equals cosine x is that wave. Something between negative 1 and 1, but it's oscillating back and forth. So this now is a good time to use the squeeze theorem for sequences. We can trap this function, cosine of n over n cubed. Well, first of all, let me start with this. We can trap cosine of n between negative 1 and 1. Because it's like I said, if you can picture, I'll write it out over here, the graph of y equals cosine of x. Graph looks like this, going back and forth between 1 and negative 1. It's oscillating back and forth. So right now, this limit in the numerator does not exist over infinity. Okay, but so I'm going to try squeeze theorem. So cosine of n I know is between negative 1 and 1. So if I want to divide that by n cubed, that's fine. I can just divide across the board here by n cubed. I'm keeping in mind that n is definitely a positive integer. So I'm dividing by a positive quantity. So I don't need to reverse the order of the inequality or anything. So now if you take the limit as n approaches infinity of negative 1 over n cubed, so that's finite number over infinity, that's going to 0. Same thing here. Limit as n approaches infinity of 1 over n cubed. Finite number over infinity, that's going to 0. And so since these limits agree as n approaches infinity, they're both approaching 0, then the limit of this function in the middle must also approach 0. And so this example number 2 also converges to 0 by that squeeze theorem.